Hello friends, today we will see our next topic, that is N-type semiconductor. So in previous module we covered that how the P-type semiconductor it becomes formed. So in P-type semiconductor we use the acceptor impurity, that is nothing but the trivalent impurity. But to design the N-type semiconductor we will going to use the donor impurity. So the material which is being used as impurity in the process of doping is called as a dopant. Okay, and when the dopant is a pentavalent atom, okay, when the dopant is a pentavalent atom, that is the atom which contain a 5 valence electron, then it is called as the donor impurity. Like in acceptor we accept, while in donor impurity we donate. So that's why the name is donor impurity. To form the donor impurity we use which type of the material? Pentavalent atom. Okay. So this pentavalent, it is used to manufacture this N-type extrinsic semiconductor. So if we consider the example, we can say the arsenic, phosphorus, antimony that we are going to use to make this N-type semiconductor. Then again the same process, what? When the pentavalent impurities such as we can say the arsenic, phosphorus, okay, is added with the pure silicon crystal, then it becomes the N-type semiconductor. So when a pentavalent impurity such as this phosphorus is added to the intrinsic semiconductor, so what will happen? The 4 valence electron of this phosphor atom, it form the 4 covalent bond of this silicon crystal. So this phosphorus, it has the 5 valence electron, while silicon it has a 4. So it will make the bond in between these. So what will happen? Out of this 5, what will happen? The 1 will remain as it is. Yes. So this, the 5th electron of the atom, it does not have a chance to form the covalent bond. So this is an additional valence electron which can enter into the conduction band very easily. To make it, it is a free electron. So thus corresponding to each impurity atom, and extra electrons become available for the conduction. So when we apply an external DC voltage, then the N-type material, then these free electrons, it should be moved towards the positive terminal of the source, okay, and it constitute the current. So what we can say in N-type semiconductor, majority charge carrier is nothing but the free electron. Like in P-type, majority charge carrier are hole. So this already I explained. So what we can say, the majority of charge carriers in N-type semiconductor are electron. Holes are minority carriers in N-type semiconductor. And in the N-type of the semiconductor, the electron density is much greater than the hole density. So when we compare with the P-type and N-type semiconductor, what we can say? When a trivalent impurity is added to an intrinsic semiconductor, it forms P-type. Here we use a pentavalent impurity. To obtain the P-type semiconductor, trivalent impurity, gallium, aluminum, gallium, indium we can use. While here we can use the PSB, ASBI, boron. Then the elements of the group 13 are added as a doping element to form P-type. The elements of group 15 are added as a doping element to form N-type. This is also we can say P-type, it is called as the acceptor impurity. This is called as a donor impurity. Okay, in a P-type the doping element is a trivalent, while here pentavalent atom. Hence see here, this is called as a donor impurity, this is called as the acceptor impurity. Holes are, this is very important, holes are the majority charge carrier. Here electrons are the majority charge carrier. While exactly opposite, minority in P-type, minority are electrons. In N-type, minority are holes. And this is very important parameter, that in p-type semiconductor the conductivity is due to the presence of holes, and in n-type the conductivity is due to the presence of electrons. Thank you.